Hello, this is Dr. Armand again, bringing you another exciting lecture on in general chemistry. Today we'll be looking at cell potential. So how do we calculate the cell potential for a galvanic cell? Also, how do we determine which species are stronger oxidizing agents or stronger reducing agents when looking at the reduction potential table? And we're going to be looking at examples of that. So sit back, relax, and enjoy the show. This is a continuation. This is part two. Part one was over redox reactions and talking about writing the shorthand notation for electrochemical cells. So let's go ahead and get started. So with electrochemical cells, we need to calculate the cell potential. So how much voltage is produced when you make this particular type of electrochemical cell. And again, galvanic cells are spontaneous, meaning they're always going to have a positive voltage. And so cell potential, or sometimes referred to as the voltage of the cell or the electromotive force, is the difference in electric potential between the two electrodes. And when the E of cell is greater than 0, it's a spontaneous process. So that tells you delta G is going to be negative, K is going to be very large. And for galvanic cells, they have E of cells that are positive, so they're all spontaneous reactions. And so the way we calculate the E of cell, or the cell reduction potential, is by using the standard cell potentials of the half reactions that occur. And these are measured at specialized conditions. The temperature is 298, and 1 atmosphere for pressures, 1 molar solutions for aqueous. The unit we use to talk about cell potential is the volt, which is the SI unit for electrical potential. Another SI unit involving electrochemistry is the coulomb, which we'll talk about later, but it's the SI unit of electrical charge. So we use these standard cell potentials to determine the cell potential of an electrochemical cell. So just to let you know, 1 volt is 1 joule per coulomb. So how do we determine the E of cell? Well, we take the E of cathode reduction minus the E of anode of oxidation. But this is what you have to remember, is that the standard electrode potential refers to the half reactions written as reduction. So what you have to do is either you can rewrite this. Let me see if I have it. No, let me go back. You can rewrite this as the E of cell was E of reduction So if you just remember that the E of anode of oxidation is actually the negative E of anode of reduction, and then this becomes E of cell equals E of cathode reduction plus E of anode of reduction. And that's how you can use the reduction potentials to determine the E of cell. So it's going to be E of reduction of cathode minus the E of reduction, E of oxidation of anode, or since the E of oxidation of the anode is equal to the negative E of reduction of the anode, so we place that, we get E of cathode reduction plus the E of anode of reduction. And so the way we determine these cell potentials is by using a standard hydrogen electrode as a reference cell, which consists of an inert platinum electrode, has hydrogen gas at 1 atmosphere bubbling through it, and is immersed in a 1 molar strong acid solution. And so this is our reference electrode, which has 0 voltage. So it's how we can determine the cell potential of everything else. So if hydrogen is oxidized, then the E of cell equals E of cathode minus E of anode, which equals the E of reference minus E of unknown, which is 0 minus E of unknown, and we get the negative of the reduction potential of the unknown solution. If H plus is reduced, again, we still, since the E of reference is 0, any electrical voltage measured is going to be due to the other species, and that's how we determine the reduction potential. So for example, if we take H plus to H2, it's a reference voltage, it's 0, let's say reduction occurs, and then zinc gets oxidized. We don't know its reduction potential, but when we measure the voltage of this electrochemical cell, we get the E of cell as 0.76. So therefore, we can determine the E of reduction of zinc. So the E of reduction of zinc is negative, or zinc 2 plus is negative 0.76. So zinc prefers to be oxidized rather than reduced. And that's how you can determine these cell potentials, is by comparing it to the reference electrode of hydrogen. And so this is a table of reference electrodes. You'll see here that hydrogen is highlighted in blue because that's kind of the border between species that like to be oxidized versus species that like to be reduced. And as you go up, these become stronger oxidizing agents. So they like to be reduced. And as you go down, the more negative the voltage, so the more positive the voltage, the stronger the oxidizing agent. The more negative the voltage, the stronger the reducing agent. So again, the more negative the reduction potential, the stronger the reducing agent, the more likely those species want to be oxidized. The more positive the reduction potential, the stronger the oxidizing agent, so those species would rather be reduced. And so that's how you get the two extremes. So fluorine gas is the strongest oxidizing agent listed in this chart. It has the most positive cell potential. And lithium ion is the strongest reducing agent, or excuse me, lithium. So the products are reducing agents, the reactants are oxidizing agents. So the stronger reducing agent is lithium. The strongest reducing agent listed here is lithium. The strongest oxidizing agent is fluorine. So again, reactants are oxidizing agent in the cell reduction potential. And in the cell reduction table, products are reducing agents. So lithium is the strongest reducing agent out of all the products shown, and fluorine is the strongest oxidizing agent out of all the reactants shown. And so again, it always prefers the stronger reducing agent reacts with the stronger oxidizing agent to the weaker. So now let's say we want to calculate the cell potential of the following redox reaction. So what we have to do is determine the which species is being oxidized, which species is being reduced. And so you'll notice here nickel 2 plus goes to nickel, so nickel is being reduced. Magnesium to magnesium 2 plus is being oxidized. And so typically it's the E of reduction of cathode plus the E of oxidation of anode. And so these are the cell potentials. So since magnesium is being oxidized, we have to switch it. I think I made a mistake earlier in that equation. No, it didn't, because the E of, no, it did. E of cathode plus E of anode equals E of cell. So that's the equation. And so if we're using reduction potentials, then E of cell equals E of cathode reduction minus, no, let's just use that one, not make it complicated. So it's the E of cathode plus E of anode. And so magnesium is being oxidized, so we should write it as Mg gives Mg 2 plus 2 electrons. And so the E of oxidation would be positive 2.37. So magnesium is the stronger reducing agent, and nickel 2 plus in this case is the stronger oxidizing agent. So again, magnesium is the stronger reducing agent because it has the more negative cell potential. Nickel 2 plus is the stronger oxidizing agent because it has the less negative cell reduction. So now to find the E of cell, it's simply negative 0.25 plus 2.37. 2.12. So this is a galvanic cell. It's spontaneous. It has a positive voltage. Also, we can say again, magnesium, the stronger reducing agent, nickel 2 plus, the stronger oxidizing agent. And again, with the way we know that is because the reduction potential for magnesium 2 plus is a lot more negative than nickel 2 plus, so that tells us magnesium would rather be oxidized than reduced. So how do we determine the relative strength of oxidizing and reducing agent? The more positive the E value, the E reduction value is, the more readily the reaction wants to occur. So again, as we get more positive, stronger oxidizing agents. The species in the agent wants to be reduced. So for example, copper 2 plus reduction potential is 0.34. It's the strongest oxidizing agent because copper 2 plus, will, out of these three given, readily wants to be reduced. So again, oxidizing agents are reactants. In reduction potential. Now, as you go down, the more negative the reduction of cell potential, the more likely that the product wants to be oxidized. So stronger reducing agent, species in the agent wants to be oxidized. These are going to be products in the reduction half reactions. More negative against oxidizing agents, more positive. So if we were to categorize, let me erase my drawings. So the strength of the oxidizing agent decreases from top to bottom. So what that means, copper is the strongest oxidizing agent, followed by hydrogen plus, followed by zinc 2 plus. Notice that these are all reactants for oxidizing agents. So copper has the most positive potential. It's going to be the strongest oxidizing agent. Now, if we look at the reducing agents, these are going to be products. And it increases from top to bottom. So as you get more negative cell potential, it means it's a stronger reducing agent. So zinc is the strongest reducing agent because it has the most negative cell potential, and copper is the weakest reducing agent because it has the most positive cell potential. So here's a chart that you can see how the strength of oxidizing and reducing agents compare. Now, when you write a galvanic cell, it's always going to, the species are always going to react in whatever way they're the strongest as. So, for example, if you use copper solid and zinc 2 plus, that reaction will not occur because zinc prefers to be oxidized and copper prefers to be reduced. But if you use copper 2 plus and zinc as reactants, then that reaction will occur because copper 2 plus prefers to be reduced, zinc prefers to be oxidized. So we're given the following reduction potentials. Which were the following is the strongest oxidizing agent? So strongest oxidizing agent means the species in this agent wants to readily be reduced, which means it's going to have the most positive cell potential. So the most positive cell potential in this case is lead. And also oxidizing agents are reactants in the half reactions. So the oxidizing agents are going to be one of these reactants. And so the strongest oxidizing agent is lead 2+ because it has the most positive cell potential. Now, the strongest reducing agent would be the exact opposite. Let me write that in green to kind of distinguish. So this agent wants to readily be oxidized. It has the most negative cell potential. We're talking about the reduction potentials. I'm sorry I didn't make that clear on the. And these are going to be products in the half reaction. We're talking about the reduction half reactions. And so these are going to be products. Let me change that to green. These. So which one is the most negative? That's going to be magnesium. So that's how you determine which one is the strongest oxidizing agent and which one is the strongest reducing agent. So we want to use values to write spontaneous redox reactions. So again, we have zinc reacts with copper 2+. You have zinc 2+ and copper solid. So again, it always goes from the stronger side to the weaker side. So zinc is a stronger reducing agent than copper because it's further down on the reduction table. It has a more negative reduction potential, zinc 2+ does. And copper 2+ is a stronger oxidizing agent than zinc 2+, and that's because its reduction potential is more positive than zinc 2+. So it's going to go in this direction, which means delta G is going to be negative, and K is going to be greater than 1. So now if we look at chlorine reduction potential and nickel 2 plus reduction potential, we want to write a reaction that will be spontaneous. And so what you have to notice is that chlorine, Cl2, has the more positive reduction potential. So chlorine is the stronger oxidizing agent. We'll call it SOA, strongest oxidizing agent, then compared to nickel 2 plus. So Cl2, do that. So Cl2 is going to be a reactant. And since Cl2 is the strongest oxidizing agent, nickel is the strongest reducing agent. Nickel solid. Because it has the nickel 2 plus has the more negative reduction potential, that means that nickel is the stronger reducing agent. And then we're going to produce 2Cl minus plus Ni plus 2. And this will be a galvanic cell, because if we look at the E of cell, it'll be 1.36 plus 0.25. And that will give us 1.61 volts. So nickel is the SRA, strongest reducing agent. Because again, the nickel 2 plus reduction potential has the most negative, the more negative reduction potential. So we reverse it and we get this reaction. So basically what I just said. When you reverse it though, you got to flip the sign. So this should be positive 0.25 because we switched this reaction. So E of oxidation. The E of oxidation of nickel is positive 2.5, 0.25. So you get 1.61. So I just did what they did here, negative and negative makes positive. The same thing I did. So now if we have 10 half reaction, 10-2 plus half reaction, and silver plus half reaction, we want to write a spontaneous reaction for this. Well, we look here, which one has the more positive cell reduction potential? Is going to be this one, so that means silver plus is the stronger oxidizing agent, SOA, because it has the more positive cell potential. 10 is going to be the strongest reducing agent because it has the most, the 10-2 plus has the more negative cell reduction potential. So the reaction will be Ag plus Sn yields Sn plus 2 plus Ag solid. E of cell would equal 0.8 minus a negative 0.14 equals 0.94 volts. Because again, you got to make it negative to get the oxidation. That's why it's minus a negative. So that would be a spontaneous reaction. So now we want to calculate the cell potential for each of these reactions and determine whether it's spontaneous. Again, if it's spontaneous, the E of cell will be positive. So we look at the first one, we see silver is oxidized, copper is reduced. So copper is 0.34 minus silver is oxidized minus 0.8. And we get wait a second. Yeah, that's right. We get negative 0.46 volts. So this is a non-spontaneous reaction. And the reason is because silver plus would rather be reduced than oxidized, because silver plus has the stronger or the more positive reduction potential. So silver plus is the stronger, the SOA, the stronger oxidizing agent, and copper is a stronger reducing agent. So the correct equation should be Cu solid plus Ag plus gives us Ag solid plus copper 2 plus. And you'll see here that the E of cell would be 0.8 minus a negative 0.34. No, sorry. Just minus 0.834. And so we get a positive 0.46. Now we look at chlorine plus chlorine gas bubble through a solution of iron 2 plus. We get chloride and iron 3 plus. Again, E of cell. Chlorine is reduced. That's our E of cathode. And then iron 2 plus is oxidized. So we minus 0.77. So we get 0.57 volts. Which means it's spontaneous. So again here, if we were to write the shorthand notation, it would be, so we use it inert electrode, platinum, Fe2 plus, comma, Fe3 plus, salt bridge, Cl2, gas, Cl minus, and then another inert electrode. So again, iron 2 plus is the stronger reducing agent, so it's our SRA. Chlorine gas is the stronger oxidizing agent. And the reason it is because it has the more positive reduction potential. Fe3 plus means that Fe2 plus is a stronger reducing agent because it has the less positive reduction potential. Now, if we were to write the shorthand for the correct equation for the above one, it would be copper 2 plus, silver plus, silver. So copper would be the anode, silver cathode. Alrighty. So now we have a voltaic cell, houses the reaction between aqueous, bromine, and zinc. It gives us the redox reaction says the E of cell is 1.83. Calculate the E of reduction of bromine if the E of reduction of zinc is 0.76. Oops, my bad. So remember, E of cell equals E of reduction plus E of oxidation. And so in this, we see that Br2 is being reduced. But we don't know its reduction. And we know that zinc is being oxidized. We know that the E of reduction of zinc is negative 0.76. So the E of oxidation is 0.76. Change the sign. So now to find the E of reduction, equal E of cell minus E of oxidation. 1.83 minus 0.76. So E of reduction of Br2 equals 1.07 volts. And this E of reduction of zinc is negative, and you got to flip the sign to make it positive. So now we have a voltaic cell involving aqueous bromine and vanadium-3 ions, has a cell potential of 0.73. What's the standard electrode potential of the reduction of VO2 plus to vanadium-3 plus? So what we got to do, remember here, is that bromine is reduced. So we have Br2 plus 2 electrons gives us 2 Br minus. And from the above equation, we know the E of reduction is positive 1.07. Then we know that vanadium is oxidized. It goes from 3 plus to plus 4. So we have vanadium 3 plus VO2 plus. Oxygen is negative 2. Plus 3 doesn't change. Well, somehow, in some weird way, it has to lose some number of electrons. So we need to know the E of oxidation of this. Plus 6. Maybe it loses, I don't know. Yeah. So anyways, E of cell equals E of reduction plus E of oxidation. So therefore, if we know the E of cell, which is 0.73, equals the E of reduction, which is 1.07, plus E of oxidation. So E of oxidation, 0.73 minus 1.07. And it's negative 0.34. And so the E of reduction of this is going to equal the negative E of oxidation, which is 0.34. So that's the E of oxidation of the, or excuse me, the E of reduction of vanadium 3 plus let me see. Let me just check, see what the charge of vanadium is. Oh, duh. Silly me, it loses one electron. My bad. I was having a brain freeze. So this should be one electron. So it oxidizes this because vanadium here is plus 4. I had a brain freeze for a moment. That makes a lot more sense. That was a long day, I guess. So this is how you calculate the cell potentials of redox reactions. Now that concludes part 2 of the chapter on electrochemistry. We talked about what cell potential is, how to calculate cell potential, the difference between how can we qualitatively or relatively assign which one is stronger, oxidizing, reducing agents. Again, oxidizing agents are going to be the reactants in the half reaction. Reducing agents are going to be the products. Also, we learned how to calculate cell potential of electrochemical galvanic cells or electrochemical cells. And so the last bit of this, which is going to be in part 3, deals with calculating the cell potential using equilibrium constant, calculating the cell potential at non-equilibrium conditions, and looking at electrolytic cells. So on that note, I hope you enjoyed the lesson for today. If you did, hit the like button, or if you learned something new, also hit the like button as well. Until next time, Dr. Armand signing off.